Welcome to this deep dive into arrays, a fundamental programming concept. Arrays are powerful data structures that help us organize and manage collections of related data efficiently. Understanding arrays is crucial for building robust applications and handling information effectively in any programming language. We'll explore one-dimensional, two-dimensional, and jagged arrays, offering diverse data structure. We'll also learn to iterate through these using the versatile for each loop. This simplifies data access and processing, making your code cleaner and more effective. Arrays function like organized containers, holding multiple values of the same data type. This uniformity makes it efficient to handle large collections of related information. It ensures data consistency and simplifies operations across the entire set of elements, which is vital for structured programming. Let's start with one-dimensional arrays, or 1D arrays, the simplest form. These foundational arrays provide a linear structure for storing data. They are intuitive to grasp and essential for building more complex data structures, forming the basis of many programming solutions. Imagine a 1D array as a single list or row of items. Each item has a unique position or index, starting from 0. For example, the first item is at index 0. This zero-based indexing provides a precise way to locate any element within the array. An array of integers might store test scores 85, 92, 78, 95. Each score is placed at a specific index. This allows for easy retrieval and manipulation of individual scores or the entire collection, demonstrating the practical utility of 1D arrays in managing numerical data efficiently. To declare a 1D array, specify its data type, like int or string. Follow this with empty square brackets, signifying an array. Finally, provide a meaningful name, such as scores. This clear syntax informs the compiler about the array's type and purpose. You can initialize a 1D array with values directly, like string, fruits equals apple, banana. Alternatively, define its size, allocating memory for elements. For example, int numbers equals new int 5 creates an array for 5 integers, initialized to their default value, typically 0. Accessing elements is straightforward. Use the array name followed by the index in square brackets. For example, numbers 0 retrieves the first element. Remember, arrays are 0-indexed, so numbers 0 refers to the first item. This precise indexing allows for efficient data retrieval and modification. Next, let's elevate our understanding to two-dimensional arrays, or 2D arrays. These arrays introduce an additional dimension, allowing us to represent data in a more complex, grid-like structure. This opens up many new possibilities for organizing information. Think of a 2D array as a grid or table with rows and columns. This structure is perfect for representing data like a spreadsheet, where information is organized in cells. It's also ideal for game boards, matrices, or any scenario requiring data in a two-dimensional layout. Each element in a 2D array is identified by two indices, one for its row and one for its column. The first index specifies the row, and the second specifies the column. This dual-index system allows for precise addressing of any cell in the grid, ensuring you can access any piece of data with accuracy. Declaring a 2D array involves two sets of square brackets, like int, comma, matrix. You specify the data type, followed by comma, where the comma indicates two dimensions. This syntax clearly tells the compiler that you are creating a multi-dimensional array with both rows and columns. To initialize, you might use int, comma, grid equals new int 3, 4, for a grid with 3 rows and 4 columns. This statement allocates memory for a 3 by 4 grid of integers. The first number, 3, represents the rows, and the second, 4, represents the columns, establishing the exact size and shape. Accessing an element requires both indices, for example, grid 0, 0, for the top left element. The first index refers to the row, and the second to the column, both starting from 0. This precise coordinate system ensures you can pinpoint any data point within your two-dimensional structure. Now, let's delve into jagged arrays, which offer more flexibility. These arrays introduce a unique level of adaptability, allowing for structures not achievable with traditional multidimensional arrays. Jagged arrays are useful when dealing with collections where inner structures have varying sizes. A jagged array is essentially an array where each element is itself another array. The key feature is that these inner arrays can have different lengths. This allows for highly irregular and dynamic data structures, unlike the fixed rectangular shape of 2D arrays, providing greater flexibility in memory allocation. Think of it as a bookshelf where each shelf can hold a different number of books. One shelf might have 5 books, another 2, and a third 10. This perfectly illustrates how a jagged array allows its inner arrays to vary in length, providing immense flexibility in data storage and organization. To declare a jagged array, use 2 sets of square brackets, but the second set is empty, like int jagged array. This signifies an array whose elements will be arrays themselves. Their specific lengths are not yet defined, allowing for crucial flexibility later on in your program's execution. Initialization is a two-step process. First, define the number of inner arrays. For example, int jagged array equals new int 3. Then, initialize each inner array individually with its own length. This allows each shelf to have a different number of books, providing dynamic sizing for each subarray. For example, jagged array 0 equals new int 5 creates the first inner array with 5 elements. This allocates space for 5 integers within the inner array at index 0 of the main jagged array. This demonstrates how you assign a specific, independent length to one of the inner arrays dynamically. Accessing elements in a jagged array also uses 2 indices, but they are separate. For example, jagged array 0, 2 accesses the third element of the first inner array. The first index selects the inner array, and the second selects the element within that specific inner array. This two-level access reflects the array of arrays structure. Finally, let's explore how to iterate through these arrays using the for each loop, a powerful and convenient construct. This loop simplifies traversing collections, including all array types. It makes your code cleaner and more readable by abstracting away manual index management. The for each loop iterates over collections, executing code for each element without needing to manage indices. It automatically handles iteration, eliminating manual tracking of positions or loop boundaries. This significantly reduces common programming errors like off-by-one mistakes, leading to more robust code. For a 1D array, the syntax is simple. For each, you declare a temporary variable, number, which holds each element during iteration. The in keyword specifies the array. This clear structure makes it easy to understand and implement, enhancing code readability and maintainability. This loop automatically goes through each number in the numbers array. This automated iteration makes your code cleaner and less prone to off-by-one errors or out-of-bounds exceptions. It simplifies array traversal, allowing you to focus on the logic applied to each element. Iterating through a 2D array with for each is possible, but it treats the array as a single, flattened collection of elements. It processes each element sequentially, from the first row's first element to the last row's last element, as if they were all in one long list. This means you lose the row and column context. You would write for each to access each individual element. The element variable sequentially takes on the value of each integer stored within the grid array, one by one, until all elements are processed. This provides a quick way to access every value without managing row and column indices explicitly. For jagged arrays, use nested for each loops. This is the most effective approach given their array of array structure and varying inner lengths. It allows you to correctly traverse both the outer array, which holds the inner arrays, and then each individual inner array, adapting gracefully to their different sizes. The outer loop iterates through each inner array, and the inner loop iterates through the elements of that specific inner array. The outer for each selects an inner array, then the inner for each processes all elements within it. This hierarchical approach ensures comprehensive traversal of the entire jagged structure. This allows you to handle the varying lengths of the inner arrays gracefully. Since the inner loop only iterates over the elements of the currently selected inner array, it automatically adapts to its specific length. This eliminates manual length checks, making your code more robust and easier to maintain. Understanding 1D, 2D, and jagged arrays, along with the for each loop, provides a solid foundation for managing complex data structures. These concepts are crucial for effectively manipulating data in real-world applications. Mastering them will significantly enhance your problem-solving capabilities and prepare you for advanced programming challenges. Keep practicing these concepts, and you'll soon master array manipulation. Experiment with different array types. Try implementing various iteration scenarios, and challenge yourself with small projects. Consistent practice and hands-on experience will undoubtedly make you proficient in handling diverse data structures, boosting your programming skills significantly.